Welcome, everyone. For today's prep, we're going to see how we can use definite integrals to help us calculate the area under the curve. And before we do, just a little bit of terminology. So we use this phrase area under the curve or region under the graph, and just want to kind of discuss what such a region looks like. So we've got a typical graph, y equals f of x, just some function here. And we're going to be looking at regions starting at some x value. So we might have a left edge given by x equals just some number a. And then we might have a right edge given by some number x equals b. And when we talk about the region under the graph, we're talking about the region that sits underneath the curve. So the curve is kind of giving us the top edge of our region here. It's bounded above. The region is bounded above by our curve. And the lower edge is the x-axis. So what we're going to be doing is we're going to be figuring out the area of this region, which goes from our curve down to the x-axis. And we're looking at just the section in between these two kind of left and right vertical lines. So we've got the left vertical line x equals a. It's kind of giving us this left edge. And then x equals b is the other vertical line. That's giving us the right edge. All right, so this is the area that we're going to see how to calculate. And it turns out that, well, just a couple things we need. So for our discussion here, our function f is going to be continuous on that closed interval from a to b. We don't want any jumps or breaks in the graph. And for the discussion we're going to do initially, we want this function to be above the x-axis. So we want it to be non-negative on the closed interval. So you can really think of this as the curve is above the x-axis. We'll see how to generalize it so that, we can talk about functions that go below the x-axis and all of that. But for right now, we're just looking at curves that are above the x-axis. And the result that relates this all to integration is if f is a continuous function, so there's no jumps or breaks, and it's a non-negative function, meaning it's above the x-axis, on that closed interval from a to b, well then the area for that region is just the definite integral going from a to b of our function f of x. So we can just integrate our function from a to b. And again, the thing we need here for this to work is f of x has to be above the x-axis. So we just want to keep that in mind. So when we're doing this, you kind of want to picture the integration from a to b here as kind of like the width of our region, and then the function f of x is the height of our function. So the limits of integration here are really kind of describing the width, and f of x is giving us the height. So what we're doing when we talk about area under the curve is we're kind of doing the area of a kind of a distorted rectangle almost. So if we go back up, everything's rectangular here. Left side, right side, bottom side. That's kind of looks like a regular rectangle. But now we've distorted the left edge or the upper edge of this region. And so, it might have all sorts of curves and weird shapes to it depending on what our function looks like. So when we set up the integration, you want to think of the limits of integration as describing the width of the region. And then the function itself is describing, how high that region goes throughout that interval. All right, so let's get a little practice just calculating a few different areas. So the first example we're going to look at is this function 3x plus e to the x. And we're looking at the region from x equals 1 to x equals 2. So if you're in Math 121, this is not example 1. This is actually example 3. So just kind of jump down and then we'll come back up. Okay, so how do we find this area? Well, first thing, we can just kind of look at what the graph of this function looks like. And we've got our function f of x plotted. And what's the region? What's the width of the region? So we're looking at this section going from x equals 1 to x equals 2. So again, this is going to be our width. So if we plot that, let's kind of sketch what the region looks like. X equals 1 is going to give us the left edge. X equals 2 is going to give us the right edge. And then we're figuring out the area for this region that goes from our curve down to the x-axis. And we're going to be figuring out the area for this region here. So that's what our region looks like. And what we see is that this graph does not have any jumps or breaks in it. And it's above the x-axis on this section of the x-axis. Going from 1 to 2, the graph is above. So what we can do is just integrate. So to get the area, we're just going to set up the definite integral. So it's going to be the integral from 1 to 2 of f of x. We can fill in our function. So we're integrating from 1 to 2, 3 over x plus e to the x. And now we just have to calculate this definite integral. So this is what we've looked at. How do we do this? Well, we get the antiderivative of each of these pieces. So for that first piece, the 3 over x, the 3 is a constant multiple. So it just kind of stays in front. And really, you can think of this 3 over x as 3 times 1 over x. So again, the 3 is a constant multiple, so it just kind of stays there in front. And we just have to remember, what's the antiderivative of 1 over x? And that's one of our special ones. That's the natural log of absolute value x. Okay, so that's the antiderivative of that first piece. Now we go on to the second piece, the e to the x. We have to get the antiderivative there. And e to the x is special. It's its own antiderivative, just like it's its own derivative. And because our function had a plus sign, our antiderivative is going to have a plus sign. All right, so we have the antiderivative. So for definite integrals, then we put this vertical line at the end, which means we're going to evaluate. And the last part of this is just to, well, do the evaluation. So to kind of make sure we get all the subtraction correct, it helps to set up a nice, kind of set up the framework here for your evaluation. So one big set of parentheses for what we get when we plug in x equals 2. And then another big set of parentheses for what we get when we plug in x equals 1. So if we do that, let's get the 2 in there first. So we get 3 times natural log absolute value 2 plus e squared. So again, wherever I see an x here, I'm plugging in 2. And then I do the same thing for x equals 1. Wherever I have a 1 here, I'm going to, wherever I have an x there, I'm going to plug in 1. So we get 3 times natural log absolute value 1 plus e raised to the power 1. And not too much to simplify here, other than natural log of 1 is just 0. So this ends up simplifying to just 3 natural log 2. I don't need the absolute value sign anymore because absolute value 2 is just 2. Then I've got my plus e squared, and then I've got minus e. And we don't normally write e to the power 1. We just leave off that exponent 1. And that looks good. So that's our, whatever that is, that's our area. So really, if we know our function's above the x-axis, and there's no jumps or breaks in it on our interval, then it's just a simple definite integral. All right, so let's try one more. Let's look at example 2. So we have a piecewise function here. And the piecewise function, f of x is equal to x on the piece where x is less than or equal to 2. And the function is equal to 2 on the piece where x is greater than 2. And we're looking at the region where a is 0 and b is 4. So again, let's kind of picture what this looks like. So we have the graph of our function plotted out down here. And you can see we have the first piece plotted. So this is y equals x. And then we have the second piece plotted. This is just the horizontal line 2. And what is our region going to look like? Well, we're going from 0 to 4. So again, that's describing the width of our region. So we're going from 0 to 4. And we're between the x-axis and our curve. So it's this region here. Now the issue with piecewise functions is we're gonna do this one actually two ways. So the first way is, well, just some simple, well, we'll probably do that second actually. Simple geometry. This is a triangle. This is a square. So we can quickly figure out the area, but we'll see how to do it with integration too. So the issue with piecewise functions is when we go to set up our definite integral, we're going to have to split our integral apart to kind of handle each of these pieces separately. And that's kind of follows the same logic as how you might do this with triangles and squares. We're going to break this region up separately into a triangular region and into a square region. So the idea of splitting up the integral, very natural type thing to do, even if we were just kind of dealing with the geometric shapes here. So let's try the integration first. So the area of our function is going to be the integral from 0 to 4 of f of x dx. Now the issue here, again, this is a piecewise function, and the pieces of this piecewise function kind of split apart at x equals 2. And 2 is in between these two values. So what we're going to have to do is we're going to have to split up this integral. So we're going to have to split up the integral. We're going to do the integral from 0 to 2 of f of x. And then, separately, we're going to do the integral from 2 to 4 of f of x. And this is one of our properties of definite integrals. If we're going from 0 to 4, well, we can kind of break halfway or anywhere in the middle. So we can integrate from 0 to 2, and then we can finish going from 2 to 4. So this is a perfectly fine thing to do. So you can think of it graphically as we're figuring out the area from 0 to 2, and then we're figuring out the area from 2 to 4, and then we're just adding those together to get the total area. That's really all we're doing. Okay. So for this first integral here, we're looking at the x values that are between 0 and 2. So here we're dealing with x values that are less than 2. So which piece of our piecewise function do we need to use? Well, we look for the x less than 2 piece, and we see that right here. So that first integral from 0 to 2, we can now replace the formula with x. So we know that when x is less than 2, this function f of x is that first piece. So we can replace that with the formula. All right, so what about the second integral here? Here we're going from 2 to 4. So again, all the x values, as we go from 2 to 4, all the x values that we're using are going to be bigger than 2. So we're looking at x values that are bigger than 2 for this integral. And if we go up to our piecewise function, x greater than 2 means we're going to be using the second piece. So we can figure that out. So we're going from 2 to 4. We've got f of x. And now we know that for this interval, our function is the second piece. So for that integral where we're going from 0 to 2, we use the first piece. And when we're going from 2 to 4, we're using the second piece. All right, so now we just calculate each of these separately. So first of all, antiderivative of x. This is x raised to the power 1, so we can just do basic power rule. So we add 1 to the exponent, take the new exponent, put it in front. So that's our antiderivative. Then we're doing a definite integral. So we put our vertical line and the limits of integration. And then we do the evaluation. So when we do the evaluation, top number goes in first. Then we subtract, and the bottom number goes in second. So when we plug that 2 in, when we plug the 2 in there, we're going to get 4 divided by 2, which is 2. And when we plug the 0 in, we're going to get 0 times 1/2, so just 0. So that first integral is 2. And then we calculate the second integral. So we want to get the antiderivative of the constant function 2. So we just multiply 2 by x. That's our antiderivative. We're doing a definite integral, so we put our limits of integration on, a vertical line like that. And then top number gets plugged in first, then we subtract, and bottom number gets plugged in second. So when we plug that top number in, we get 2 times 4, which is 8. And when we plug the bottom number in, we get 2 times 2, which is 4. So we end up with 4. So what we found here is 2 separate values. We found the value of this first integral, we found the value of the second integral, and now we can just kind of put these together. And we get 6 as our area. All right, so this is done with integration. But like I said, there's some simple geometry at work as well. So if we go back down, this 2 here, this is the area of the triangle. And the 4 that we found, this is the area of the rectangle, well, actually the square. So if we're looking from 0 to 2, we have that triangular region. And you can figure out the area for that triangle. Is 1/2 base times height. So the base of this triangle has 2 units. The height of this triangle has 2 units. So we get 1/2 2 times 2, which is just 2. And then for that square, we've got this square over here. And we can figure out the area for that square. And, well, we can just count up how many unit squares are inside of it, which in this case is 4. But in general, maybe if it wasn't as nice as that, it's just length times width. And the width here is 2, and the height is also 2. So we end up with 2 times 2, which is 4. So that's kind of another way to think about this. But this is if our graph produces some kind of recognizable, easy geometric shape. Otherwise, we're using this integration. So this is a nice example because you get to see kind of that property of the definite integral. When we split it up, really what we're doing is we're figuring out the area for one region, we're getting the area for our second region, and then we're just adding those two areas together to get the total area. All right, so we're going to be practicing a little bit more with these area calculations in class, so we'll see you then. Bye-bye.